Before Earth took shape, the space surrounding our young sun was a lethal, kinetic shooting gallery. The early solar system was a violent debris field of rock, dust, and gas, violently colliding in the dark. Roughly 4 billion years ago, Jupiter began to take shape. It did not assemble from the rocky silicate material common in the inner system. Instead, it captured the bulk of the nebula's leftover hydrogen and helium, forming a body more chemically similar to a star than a planet. This diagram maps the early solar disk, highlighting a thermal boundary known as the frost line. This was the specific distance from the sun where temperatures dropped low enough to allow volatile compounds like water and ammonia to condense into solid ice. Forming beyond this line gave Jupiter a massive material advantage. In the cold of the outer disk, ice was as abundant as rock is in the inner system, allowing the young planet to rapidly accrete mass and become a gravitational engine capable of dictating the survival of every other object in orbit. Starting its life at a distance of about 3.5 astronomical units, Jupiter began to drift. As it cleared a gap in the surrounding gas disk, it initiated a massive inward migration toward the sun. In this simulation of the grand Tack hypothesis, Jupiter plows inward to 1.5 AU. This sweep acts as a cosmic snowplow, truncating the inner rocky rubble and permanently stunting Mars, before Saturn's orbital resonance finally tethers Jupiter and pulls it back outward. The kinetic debris generated by this inward sweep had an even darker consequence. An entire early generation of planetary embryos was caught in Jupiter's resonances, driving them to spiral directly into the sun for total incineration. The inner solar system we recognize today was preserved by this narrow margin of safety. Had Saturn not pulled Jupiter back, the band of material that eventually formed the Earth would have likely followed those early embryos into the sun. Descending beneath the cloud tops reveals the extreme mechanics of a gas giant. This is an environment defined by exponential pressure, where the sheer depth of the atmosphere creates a crushing internal engine. Dropping deep into the interior, atmospheric pressure scales so intensely that the physical rules of matter change. Under millions of bars of pressure, hydrogen atoms are compressed until they physically cease to act like a gas. This cross-section maps the scale of Jupiter's interior. At extreme depths, the pressure forces the element into a fluid state known as liquid metallic hydrogen. In this state, the highly conductive liquid ocean allows electricity to flow like a metal wire. Because Jupiter completes a full rotation every 10 hours, this massive conductive ocean spins rapidly. This motion drives electrical currents through the planet's interior, acting as a planetary dynamo that generates a magnetic field 54 times stronger than Earth's. This magnetic field traps highly charged particles, creating a violently intense radiation belt around the planet. Measuring it required spacecraft built with heavy, specialized shielding to survive the onslaught of energized ions. This internal mechanism drives the planet's external influence. It is a massive thermodynamic engine that generates and maintains one of the most hostile, highly energized environments in the solar system. Ascending back to the upper atmosphere, we can observe the thermal exhaust of this internal heat engine. This energy vents outward, manifesting as violent, continent-sized storms churning across the cloud tops. The most prominent of these is the Great Red Spot. It is a massive, high-pressure anticyclonic storm with roots extending up to 300 miles deep into the atmosphere. Historical observations verify that this massive storm has raged persistently for centuries. It has served as a stable, observable feature of the planetary machine since humans first pointed lenses at the sky. Yet modern data reveals a shift. Measurements show the Great Red Spot is actively shrinking in size. The iconic, swirling bands of color we associate with Jupiter are merely temporary exhaust vents. They are atmospheric reactions to the shifts of a massive, churning machine hidden beneath the surface. Fast forward billions of years, our sun exhausts its hydrogen fuel. This deficit triggers a massive expansion, swelling the dying star into a devastating red giant. The outward push of extreme stellar heat will reach deep into the outer solar system. Jupiter will be subjected to levels of solar radiation it has not faced since its formation. This comparative scale model illustrates the hot Jupiter phase. As the ambient temperature of the solar system spikes, the extreme external heat will cause Jupiter's outer atmosphere to massively swell and bloat in volume. The familiar bands and spots will boil away. The planet will physically transform into a superheated, bruised purple sphere of irradiated gas. Even a towering gravitational engine is ultimately at the mercy of its host star's thermal output, forced into a radical physical metamorphosis by the heat. In its final stage of death, the Sun will shed its outer layers entirely, collapsing inward to leave behind a small, cold white dwarf. When that massive external heat source vanishes, Jupiter will experience an immediate thermodynamic crash. Deprived of solar radiation, the once dynamic gas giant will cool rapidly, hardening into a dark, completely frozen monolith. Our solar system's largest planetary engine ends as a silent, scorched behemoth orbiting a dead star.